If you have no idea about Fourier series, or maybe you know something about Fourier series, but you are really puzzled about the mathematical complexity of Fourier series, then this is the right video for you. Because in this video, I will not only answer this question, why Fourier series exist, but also I will show you the beauty of Fourier series. But before jumping into Fourier series actually, I want to discuss a concept called linear combination with you. What is a linear combination? Let's say you have three types of coins: a 1 rupee coin, 10 rupee coin, and 100 rupee coin. These are the only coins available, okay? And you want to pay a particular price, let's say 237. How are you going to pay? You will take or let's say 200 rupee coins, then 3 of the 10 rupee coin, and 7 of the 1 rupee coin, right? Now this expression is a linear combination, and in linear combination you have to understand there are two types of things. These numbers 2, 3, and 7, they are the weights. They represent the weights, the amount of coins you will have at your hand. You will have 200 rupee coin, 3 of the 10 rupee coin, and 7 of the 1 rupee coin. And this 100, 10, and 1, these guys are the units. Okay, so basically what we are doing, we have a couple of units. We take those units in a couple of combination. In this case, this combination is 237, and finally we get this price, which is 237. By the way, using these coins 1, 10, and 100, you can create any price from 0 to 999. Now I want to take you to the world of vectors. Can I say that any 3D vector can be represented as a linear combination of three unit vectors I, j, and k? Yes, I can. Why? Because I, j, k are orthogonal to each other, and we can create a table like this, where each cell of this table represents the dot product between the column and the row. And as you can see, all the diagonal elements of this table are 1, and all the non-diagonal elements are 0. So what does it mean? It means that if I have any vector and I want to find out the coefficient of that vector, for example, I have this vector a, b, c, and I want to find out what is the value of this coefficient a. All I need to do is make a dot product of this vector v with I. What it will do, it will make the dot product, it will make a dot product with all the other components I, j, and k, and they will become 0. The only term that will be left behind is a. So can I say that because all these unit vectors are orthogonal to each other, I can always find out the coefficients? And there is a link between this statement that any vector can be represented as a linear combination and the fact that these unit vectors are orthogonal. There is a very close relationship, because this orthogonality allows me to find the coefficient of any component. Now I'm going to take you to the world of waves. Well, waves are everywhere. Light is a form of electromagnetic wave. Sound is a form of mechanical wave. What is a wave really? Well, a wave is a thing, a quantity that repeats periodically over time. Now this brings us this fundamental question. For example, in case of money, we had some fundamental units, 1 rupee or 10 rupee coins. In case of vectors, we had some other fundamental units, I, j, those unit vectors, which we could use as a building block to construct any vector. Is it possible to do the same in case of wave? Are there any fundamental waves which we can use as a building block? Can any periodic function be represented as a linear combination of some unit functions? Is it really possible? Now, interestingly, it turns out that it is actually true. There are, unit waves, and they are nothing but bunch of sine waves and cosine waves. And that is all about Fourier series. Fourier series says that any function, any periodic function can be represented as a linear combination of bunch of sine waves and cosine waves. That's the beauty of it. This naturally brings the question, why is it true? It turns out that just like vectors, sine waves and cosine waves are also orthogonal to each other. Now wait a minute, what does orthogonality even mean in case of waves? For example, in case of vectors, we were making the dot product, but in case of waves, we can't do any dot product, right? Well, we can do something different. See, if we have two waves like this, we can find the value of those waves at a particular point, those two waves, and then we can multiply. And we can do similar thing for each point and add them up. Okay? This is nothing but integration. So if we create a table of integration among those sine waves, it turns out that all the non-diagonal elements become 0. So if the integration of sine 2x and sine x is 0, only the diagonal elements where we are integrating a wave with itself are non-zero, and their value turns out to be 1/2. And this is the reason Fourier series exists, because all the components of Fourier series, all the fundamental waves, sine x and sine twice x or cos x, and there are infinite of them, they're all orthogonal to each other. That means I can take any random function and I can write them in a form like this. It is a linear combination of sine x and cosines, and I can find the coefficient of any term. For example, if I want to find out the coefficient of this guy, like a1, all I need to do is integrate this function fx. First multiply fx with sine x, because the corresponding wave for a1 is sine x itself, and integrate that. Because what it will do, it will make all the other terms 0, all the other terms will disappear. The only term that's going to remain is this guy, whose value is going to be half a1, and this way we can find the value of a1. Yeah, this is the reason, this is the beauty of it. My goal in this video was to create an intuition, to build an intuition how we see waves. We think of waves as like continuous pieces, but we can actually mathematically break down any wave, any periodic function into fundamental units, and those units basically constitutes the fundamental components of Fourier series. Thank you for watching.